Kinetic molecular theory. Here we're going to do the concepts only, not the math behind it. This is trying to understand pressure, volume, temperature on a molecular level. Seeing or imagining what the molecules are doing. The kinetic side, just how fast are they moving, which relates to the energy, right? The kinetic energy. And using those concepts, you can get a good picture of why does the pressure increase when the volume decreases, for example. All right. The model, the theory, has these 5 postulates here. This I picked up and just copied directly from the textbook. Right, so, number 1, gases are composed of molecules that are continuous motion, so they're always just bouncing around on the container. They travel in straight lines and they change direction only when they collide with something else or with the walls of the container. All right, so there's billiard balls just going all over, but in 3 dimensions here, bouncing off the walls, bouncing off each other. They're moving in straight lines, and they're always moving. They always have some kinetic energy. All right. Number 2, the molecules composing the gas are negligibly small compared to the distances between them. All right, so they're really spread out. There's not a whole lot of molecules per volume of the container. Right, which means they don't collide very often. Every once in a while they're going to collide with each other, but they're really, really small compared to the size of the container and the spaces that they have. All right, which is an accurate picture of a gas, by the way. Number 3 says the pressure exerted by a gas in the container results from collisions between the gas molecules and the containers of the wall. So what is pressure, in other words? They're giving you this molecular picture of it. It's when these gas molecules, which are moving around, once in a while they bounce off each other, but they definitely hit the side of the wall. Well, if you get something, if I take a bowling ball or a billiard ball and I throw it at the wall, it hits that wall, it's going to give a force to the wall. And there's a certain square distance, area I should say, that it hits that wall on, and so again, force per area, that's what pressure is. That's what it's defined as, force per area. And so pressure, as we measure it, the pressure of a gas is due to those things colliding with the sides of the container, right? Those molecules. Number 4, the gas molecules exert no attractive or repulsive forces with each other or the walls of that container. Therefore, the collisions are called elastic. That is to say, they don't lose the energy. All right, so when they're bouncing around, once in a while they hit each other, they bounce off perfectly in an elastic collision from physics. In other words, there's no loss of momentum. There's no loss of kinetic energy. We don't have to worry about that complication. They just bounce off each other. They bounce off the sides of the wall again. No loss of energy there. Perfect elastic collisions. That simplifies things and makes it easier for us. Okay. And number 5, the kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. All right, so we get the gas hotter. How does that manifest itself? Well, the molecules start moving faster. They have greater kinetic energy. All right. That's exactly what we've talked about all along. All right, right from day 1 of the class. We are ignoring the idea that some of the temperature increase could go towards other types of kinetic energy, such as vibrations or rotations. And they say, well, we're going to ignore that. It's a minor component. It's just the kinetic energy of those gas molecules. All right, so there's our picture of this theory and what a gas would look like on a molecular point. Let's think about the different laws that we've talked about that we've used in calculations, and now we have this picture, perhaps a molecular picture of it. So number 1, Amonton's law. Remember, Amonton's law said that P over T equals P over T. That is to say, pressure and temperature were proportional to each other. As one went up, so did the other. Right? And our picture there was a steel box. You have a gas in there. You've got so much pressure. Because it's a steel box, the volume can't change. So the volume is locked in. It's sealed, so the number of moles, N, that's locked in. Right? But pressure and temperature can change. So you take the steel box and you put a flame under it, you heat it up. What happens? It says the pressure on the inside of the gas also goes up. It heats up as well. And we're going to use the kinetic molecular theory here to try to explain that. Okay. So think about the gases bouncing around inside this box. Right? They're hitting the sides. That gives you the pressure. They're going so fast, that's due to the temperature. And then we heat it up. Temperature goes up. What happens to the molecules? They move faster. Remember, we said the temperature goes to kinetic energy. Higher temperature means higher kinetic energy, which means they're moving faster. So now I've got, compared to a nice slow molecule that bounces off, now I've got one that's really bouncing off fast. Obviously it's going to put more force on it, therefore the pressure goes up. So Montan's law makes sense. As temperature goes up, pressure also does too. What about number 2, Charles' law? Well, number 2, Charles' law says that volume and temperature are proportional. So here, instead of a steel box, we put it into a balloon, let's say, and I heat it up. Here, the pressure stays constant. Think about a balloon. You've got 1 atmosphere of pressure from the outside squeezing on this balloon, and the gas is pushing on the inside walls of the balloon. Again, 1 atmosphere of pressure, and therefore the balloon doesn't continue to grow or shrink. It stays its right size because those forces are equal. Okay, and if I allow the balloon to expand or contract, whatever, that allows the pressures to again equalize when a change occurs. So, for example, take this balloon and heat it up. The temperature goes up, the molecules start moving around faster, which means now we got greater pressure on the inside. But a balloon can stretch, right? And it's going to stretch and stretch and stretch until the pressure actually remains constant. It goes back down. Why would it go down just because it's stretching? Well, because as I stretch, I've got more surface area on the inside of the balloon, but I have the same number of molecules whipping around inside, and so now the force per area, there's a greater area, and so force per area, more area on the bottom, that means pressure is smaller. And so as it expands, the pressure gets smaller until it stops expanding. Right? So Charles' law, you heat it up, it gets bigger. Right? Pressure is constant because we allowed it to expand, therefore it stayed constant, and the number of moles is also constant. So Charles' law makes sense on a molecular point of view. If I heat the gas up inside the balloon, its volume gets bigger. All right. Boyle's law says pressure times volume is constant. So as pressure goes up, volume goes down. Okay? So here we're not going to heat it up. We're just going to increase or decrease the pressure and the volume. And it says as one goes up, the other one goes down. How can we manage that? Well, think about a balloon again. It's this big. It's got a pressure and a volume. And then let's shrink the volume. So let's crush down out of here. We'll make it a smaller one. What happens? Look, I'm increasing the pressure. That made the volume go smaller. Again, as pressure goes up, volume goes down. So squeeze down a balloon. In terms of the gas on the inside, we can think about it as well. If I force a smaller volume, then again, less surface area on the inside, and so the force is being divided by a smaller area, which means pressure is higher. Pressure is force divided by area again. And so from the point of view of the gas molecules, yep, pressure increases. Smaller volume, larger pressure. That's Boyle's law. Yep. Avogadro's law, as N goes up, the number of moles goes up, so does the volume. Well, that's because there's more collisions now with the inside wall of the container. If I put more gas in there, there's more molecules hitting that same area, so there's a more force, and it's going to get bigger. So as N goes up, volume also goes up. Okay. And finally, Dalton's law, the idea that you could add the pressures together. Well, because you got a mixture now of gases inside this balloon, you could look at, well, how much pressure does just the one gas, how many times does it hit the walls of the inside? How much pressure, that is to say, how many collisions does the other gas hit that wall? And then the total collisions, well, is the total pressure added together. And so you can literally add them straight, and you get the total pressure. It's due to the collisions of the molecules of the gas with the inside wall of the container. So Dalton's law makes sense on a molecular point as well.